Assalamualaikum. This is Mustafa Shah with Awais Khan, and we are here to present a research paper that is titled with Feed Home Cloud Edge Based Personal Feed Learning for In-Home Health Monitoring। आजकल पूरी दुनिया में इन होम हेल्थ मॉनिटरिंग बढ़ती जा रही है, जिसमें IoT, मशीन लर्निंग और स्मार्ट हेल्थ केयर एक अहम किरदार अदा कर रहे हैं। पर जो एग्जिस्टिंग अप्रोचेज़ हैं वो यूज़र्स की डेटा प्रोटेक्शन पर ज़्यादा ध्यान नहीं दे रहे। But this Feed Home is a novel cloud edge-based federated learning framework for in-home health monitoring that learns a shared global model in the cloud from multiple homes at the network edges, while protecting data privacy by keeping user data locally. Let's start with the introduction to the in-home health monitoring. As the population of aging people increasing globally, so the demand for home-centric healthcare also increasing. IoT devices offers pervasive, non-intrusive health monitoring. This facilitates smart in-home healthcare. IoT devices, particularly wearable devices exemplified by smartphones and smartwatches, can track users' activity, heart rate, and then feedback these data to healthcare centers for further processing and diagnosis. And this is how the in-home health monitoring is done. The privacy challenges in health monitoring concerned by the author of the paper are data privacy concern, regulatory restrictions, and integration challenges. The data privacy concerns. The current healthcare application often utilize machine learning models trained on the massive user data. As users' health data involves individual privacy, collecting and storing abundant health monitoring data at a remote cloud center would impose great privacy leakage risk. The regulatory restrictions. With increasing concern on data security and user privacy, several regulatory policies have been set to restrict data accesses. For example, General Data Protection Regulation in the European Union has enforced strict rules on data security and privacy protection. The integration challenges. Under increasingly stringent data privacy protections, it is almost impossible to integrate sufficient user health data scattered around multiple families for machine learning model training and in-home health monitoring. There is a feed home framework proposed by the author to address the problems discussed before. As we can see in this picture, the global model is trained and maintained in the cloud. The cloud aggregates local updates from each home to improve the global model using federated learning. Here is the edge layer, also called the home gateway. Each house, like home number 1, home number 2, home N, has a home gateway which consists of local storage and computation capabilities. Local model trained on the specific home's data. Users generates health data via wearable or smart devices. This user data is kept locally and used to train, update, and personalize model using the local model received from the federated learning system. Ensures privacy as raw data never leaves the home. This federated learning process can be described as the global model is sent from the cloud to each home. Each home trains the local model using its own data. These local updates are then sent back to the cloud. The cloud aggregates all local updates to refine the global model. This cycle repeats, enabling a better global model without compromising user privacy. The generative convolution autoencoder is a novel model of the feed home to address the challenges of imbalanced and non-IID data distribution in the healthcare monitoring. This model combines a convolutional parameters encoder that learns low-dimensional representative features, convolutional decoder that calculates reconstruction loss, a multi-layer perception that predicts the likelihood of the class label. This generative convolution autoencoder generates new data samples of minority classes in low dimension space to deal with the imbalanced data distribution, allowing for the more accurate personalized healthcare performance. This lightweight model reduces communication costs and it transfers efficiently between cloud and edges. Personalization and data generation. The dimension reduction. The encoder network of generative convolution autoencoder encodes high dimension input data into low dimension, making it easier to generate synthetic samples for minority classes. Synthetic minority hour sampling. Synthetic minority hour sampling technique is applied to generate a class balanced dataset in the low dimensional space, improving accuracy in mimicking the distribution of data samples. Model personalization. The prediction model is fine-tuned with the reconstructed class balance dataset based on the user's personal data, learning the fine-grained information for personalized healthcare. The author have conducted extensive experiments using a realistic human activity dataset called MobiAct, which includes activities of daily living, fall-like activities, and actual falls. The experiment compared feed home with both traditional centralized methods and other federated learning approaches. The results shows that feed home significantly outperform existing widely adopted methods in both balanced and imbalanced data cases. For example, feed home achieves a high accuracy of 95.41% with more than 7.49% accuracy improvement over the widely used seen in algorithm. Here is the conclusion and future work of the paper. The novel framework of the paper is Feed Home Cloud based personalized federated learning framework that prevents data leakage by keeping user data locally by achieving personalized model learning. Innovative design described in the paper is the generative convolution autoencoder that mitigates performance degradation caused by the imbalanced data distribution and achieves the superior personalized prediction while reducing communication cost. The proven experiments demonstrate feed home's effectiveness in both balanced and imbalanced data scenarios with significant accuracy improvement over the traditional methods. This work can be applied to various healthcare applications like feed home is a powerful approach for the future health monitoring.